Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so thank you all for coming. This afternoon we're very pleased to have Matt Green visiting us from Johns Hopkins University, and he will be talking to us about CHARM, a framework for rapidly prototyping cryptosystems.
Thanks. Is this microphone working? Well, okay. Yeah. So yeah, I'm going to be talking about a new framework called CHARM. CHARM is a collection of ideas, some of which are new and a few of them are not terribly new. But to paraphrase somebody yesterday, I think that there's a compelling case for a lot of them. Let's pray this works. Ah, neat. So a few people have asked me if CHARM stands for something. This is kind of the stuff that comes up when you start searching for CHARM. There are many different things. My favorite is a fundamental quark that has an electric charge of plus 2/3. That's not what CHARM is. Baltimore is actually Charm City, and that's part of the reason that we chose the name. For those of you who are fans of The Wire, you should recognize the place a little bit. It's what life is like on a daily basis. So let me explain a little bit about what CHARM is, and to do that I have to explain how I got to a place where I needed to build something like this. So for the last several years I have been working on cryptography from a kind of a systems point of view. And what that means is a bunch of different things. A few years ago I was working on attacking cryptographic RFID devices like the ExxonMobil SpeedPass. More recently I've been working on things like outsourcing attribute based encryption, which we saw a lot of today, to the cloud to make it faster on mobile devices. Somewhere in the middle of my PhD, I actually kind of dropped out for a while, and I started a software security consulting business, which I won't talk about, but it does have clients, including Microsoft, so we've done pretty well with that. In my spare time, what I like to do is I like to develop new cryptographic protocols, things that provide privacy for database searches, things like adaptive oblivious transfer, and things like anonymous credential schemes that let you do access control. Then I made one terrible mistake somewhere in the middle of my PhD, which is that I told a bunch of my cryptographer colleagues that I knew how to write code. And the end result was that they liked me to implement things. I've written a few cryptographic libraries. The most recent is this thing called libfunc, which stands for the Functional Encryption Library. Now the genesis of this library was about 2 years ago, when Brent Waters came to me and said, hey, it would be a huge win if we could develop a new attribute-based encryption library that supported many new schemes and was very extensible. And I had a good motivation for this, which was that I was actually working on a new grant doing medical record security, and we thought maybe attribute-based encryption would be useful here. So we came up with this new library, and the problem is that in order to do this, I chose the worst possible language to do it in. I decided to write a new library in C. I thought this would be a few weeks worth of work. It ended up being 3 months and about 15,000 lines of code. And somewhere in the middle of that, I decided that I would never, ever write a new cryptographic library, at least in C, again, that there was something wrong with what we do. So the question that kind of came to me in the middle of this is, why is it that people are coming to me to write libraries? Why do we so infrequently do this? Why is it so hard? And the reason is that for a large part, the knowledge isn't there. The people who know how to write these crypto systems are cryptographers. We have better things to do, and we're not incentivized to implement any of our work. So that's why you see maybe 3% of all the crypto schemes that show up in Eurocrypt and crypto ever actually making it into code. We assume that somebody out there, maybe the systems community, is going to do it for us. I think that industry does do it, but if they do, they don't like to tell people about it. They don't like to release their code back into the wild, and I'm kind of looking at Kristen here, hoping that maybe I can kind of influence that. But it really doesn't happen very often. Another reason is that it's just really hard. The tools that we have are not right. We have some libraries out there, but not enough of them. For example, if you're looking to do lattice-based crypto, what tool is there to do that? I hear people using Sage, but there's no lattice-based crypto library. There are pairing-based crypto libraries, but they're not always well supported, and they're not always kind of there in the right way that you need them. But the really, really big problem that makes this so painful is that there's almost no reuse of code. And so I was talking to Sarah today about a project she did last year, and I said, so how much work have you done on that project in the last year? And the answer was, well, we fixed something a few months ago when somebody asked us. And the thing is, when people write these codes for research, this code for research purposes, they tend to kind of do it until it's not necessary anymore, and then they drop it. And it's very, very hard to take somebody else's library and use it as a building block in your own code for reasons that we can get into. So the question is, how do we solve these problems? So all these new crypto systems, just in case you're not convinced that they exist, there are things like IBE and CPABE, KPABE, group signatures, anonymous credentials, all sorts of computations on encrypted data that we want to do. So what we'd like to know is there a better way that we can make it easy for cryptographers to actually implement this code? And to paraphrase one of the big talks that we had yesterday, is there a better way for cryptographers to interface with their computers, to go directly from their research to working code with minimal effort? To show you what I mean by working code in the worst possible way, here is a snapshot of the implementation of RSA encryption taken from OpenSSL. This is page 1, by the way. Okay, so you can see OpenSSL is not really a fair example because it's probably the worst library ever made. If you look for OpenSSL in code quality, one of the first results that comes up is one called OpenSSL is written by monkeys. And it's really terrible, and we can talk about that later. But you know, it's not something that looks at all like what you think of when you think of RSA encryption. Let's see, we have page 2 on here. There we go. So the question is, why are we writing these libraries in languages like C anyway? That's not the way that other industries have gone. If you look at graphics, for example, in gaming, typically what happens is we use C when we have to. We even use assembly when we have to. We have a lower layer that does sort of optimized native engines that do performance critical tasks, and then we have a higher layer that gives you a nice API that people who are not experts in that kind of work can use to develop new things. So we want to follow that framework, and we want to build something that's kind of motivated by that idea. So our approach is this. Let's start by taking many of the complex and performance-intensive mathematical routines, let's encapsulate them, write them in C, and then provide them back to the user in a very simple way. Let's expose them to a high-level language. We happen to choose Python here. You may disagree with that. We're not married to it, but Python's a nice language for a bunch of reasons. And then, and this third bullet point is a really, really big bullet point that hides a lot of detail, let's create reusable and extensible tools that people can use to then go out and implement crypto systems and then reuse those crypto systems and build more complicated protocols on top of them. So the theory here is that we can rapidly develop new crypto systems. Instead of 3 months, we can do it in an afternoon. This slide, I sometimes get a little static on. Why Python? Not because I'm a Python fanatic. I think Python has a lot of nice features. It's object-oriented, blah, 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 blah. One thing that's really important is that it's an interpreted language, which means that you can dynamically generate code. We actually use this in a few of our systems. But there are many other things that make it useful. Many of the data structures are very, very close maps to what cryptographers think about when they say, let's output a ciphertext. They don't say, well, let's define a big ciphertext data structure. They say, let's just output these group elements and we expect them to be packed together. Python's very nice for that. So the benefits of this approach to cryptographers are that we can really focus on the crypto algorithm rather than all those implementation details. We can reduce time, and we can basically get to something that looks like as close to a LaTeX paper as we can. So here's kind of textbook RSA in Charm. Now, this may look a lot like something you'd see in Sage, but this is just kind of the example of how we want things to look in the end. So this is actually the full RSA protocol. So this is what RSA looks like. When you compare that to the C code that we saw from OpenSSL, you can see it's kind of a big reduction in code size. Yeah.
So what happens to performance then?
Right. So the question is, how much can we bury those performance optimizations so that you don't have to know about them? For example, how much can we abstract into the group, the ring interface, so that when you do this kind of exponentiation, you don't have to explicitly have separate modes that do CRT optimizations and so on. That kind of thing can happen for you, and you can flip switches. So a lot of the idea of this is that we can kind of hide those details so that no matter how much optimization you have, you get something that looks like readable code. And that's kind of the basic starting point for what we did.
But what about, is there also extra cost just from the way that the things compiled?
Is there extra cost from using an interpreted language? Yeah. And then, so actually the interesting thing is that for many of the schemes that we use, not really very much. Now, somebody who is doing very, very tight loops in Python will object that, yes, there's a call overhead in Python, and there's some overhead from going from Python to C. But the truth is, in many of the schemes that we use, particularly bilinear map schemes where we're doing pairings. A lot of the actual work is taken up by the mathematical operations. The interpretation, and it's a fairly optimized interpreter. A lot of that work, that really makes up a few percent of the total cost. So are you willing to sacrifice maybe 5% of your efficiency for something that's usable and you can develop quickly? That's a big question. I don't know the answer to that. I am, but maybe not everybody else is. So I'm not going to claim this solves every problem. Yes?
Do you have some numbers on this? Or?
We will get to numbers definitely at the end. A few numbers.
To be fair to OpenSSL, which I'm not a big fan of, you're not showing here the nasty details that OpenSSL has to deal with, because you're hiding them inside, for example, encode and decode, which has to deal with lengths, which is what OpenSSL is dealing with, right? It has to deal with verifying that the parameters match the message length and this and that. So it's buried in there somewhere. There's encode and decode you have to write.
Let me put it another way. It's buried in there somewhere, but it does not have to be buried in your RSA encrypt routine.
Well, encode does.
But it doesn't have to be there. I mean, the way that, let me put it even a different way. If you wanted to extend OpenSSL to implement a new crypto system, would you be able to do that with the building blocks that they provide for you? Is it modular enough that you can take those systems and you can extend them easily? And the answer that I've seen looking at most crypto libraries, and including OpenSSL, is it's not. It's not designed from the point of view that you want to reduce things to the smallest point.
I agree.
Yeah. Yes?
Let me see if I understand this. That description, the code on the previous thing, it's using no C code, it's using just directly Python, or is it making, on the previous slide, or is it making calls out to things that are written?
Yes, so I said before that what we want to do is we want something that's performance, that actually can perform properly. So we actually do use C code for many of the computationally intensive operations.
So Python is more of a glue language.
Exactly. But the truth is that if you look at many modern crypto systems, if you look at many of the research papers out there, the truth is that that's what you're writing, is you're writing the glue. Most of the operations, even in the lattice world, are really standard operations that are being put together in different combinations. There are a very, very small number of exceptions. So why are we writing in C? Why are we writing entire crypto systems in C when what we really want is those operations, that small set of operations, to be efficient? I'm not saying anything really new and controversial here. I'm just pointing something out that seems pretty obvious to me. Yes?
So just looking at your code, so what is it reflected that n is the product of P and Q?
On the previous
yeah, this is, sorry, that's, paramgen is actually a separate.
Oh, it's specific for RSA, it's not.
Yeah, I think there was a different one. Sorry.
Okay, I'm sorry.
Yep. Yeah, that's right there. Yeah, so this is, exactly, so there are a lot of different things. This code is actually a couple months old, so I'm not even sure how well it's been optimized, but this is pretty much what we want it to look like.
So can you comment either now or maybe later on how different Charm is, say, for example, from Sage, which is using Python?
So the idea is that, Sage does a lot of the same things at a very low level. And I'm going to talk about some of the extensions. So what I want to do is I don't want anyone to get the idea that this is it. I mean, we're not just taking Python and throwing in a few exponentiations. If that was really all we were doing, it would just be Sage. We are actually adding some extra tools that are not available in Sage, some extra crypto-specific tools. And then we're adding some other support for other capabilities that are really not there in Sage. We could have started with Sage, and we could have built on top of that. And I'm not totally opposed to that. We just felt that it was cleaner not to have to pull in all that overhead of what Sage is. So we kind of start with the basic building blocks. I'm just going to give another example because I wanted to have a couple of code examples right up front. This is one of the nicest C implementations of a crypto system I've ever seen. It's by John Bethencourt. It's a Paillier library. It's beautiful. I mean, he writes, there should be a museum in which John Bethencourt's code is, because when I write code, it doesn't look like this. But it's C code, and he wrote it around GMP. And this is what it looks like. This is page 1, and this is page 2, and this is page 3, and this is page 4. So there's a lot of code involved in doing something very simple, even though he's using a library to do all the fundamental operations. So this is what we can get to in Charm. Not saying there's anything radical and new here, but the goal is to make something that looks like what you see when you see a description of the Paillier protocol, as close as you possibly can. There are a lot of things that are going on in this code. For example, we have basic routines for generating primes, for checking them. We have some routines that allow us, just some basic Python features that allow us to pack things up. A lot of his code is allocating and deallocating memory and serializing it and putting it into data structures. We can eliminate all of that because we're working in a high-level language. So just very simple things you can do once you move away from C. So there are a lot of previous approaches to this. Many people will say, well, there are a lot of cryptographic libraries. What's the point of having yet another? There are also some things like cryptics. There are some other tools I'll talk about in a second. The problem is that these tools are really designed to work with an API. They're not designed to generate new crypto systems. They're very, very hard to extend. And they're really not designed, they're not designed to be used together. If you've ever tried to combine OpenSSL with pairing-based crypto library, you'll find that even if you're dealing with non-pairing curves, you're doing anything like that, or with Miracle, it's very hard to use those data structures together. They're not compatible. I wanted to give one more painful OpenSSL example just to drive this point home. This is a piece of active OpenSSL code. I just wanted to point out the if0 structure, in case any of you guys have seen this before. This code was not designed to be looked at. This code was designed to be used from the point of view of a very nice API. It was never designed to be updated, at least not by the people who are outside of OpenSSL. There are many existing implementations of Cryptosystems. For example, Brent hosts a page called the Advanced Crypto Software Collection, where a bunch of people have sort of dropped their implementations of things like the Paillier scheme and IBE. The problem is that many of these things aren't reusable. There's no reunifying framework for using these and so on, so I'm just covering the same things. There are many other related projects that are very close but not quite what we need. There's Cryptol, which is really designed for symmetric encryptions, very, very high performance, but the goal is to produce FPGAs, not to produce code. There's Sage, and Sage has many, many things, but it has kind of too much. There's a lot of material in Sage that you don't necessarily want to import when you're building a crypto library. Yehuda Lindell is actually building something that's related to this, but he's using Java as his base language. We're working with him on some of that, but he's taking a different approach than us, which is that he's actually designing his software, and we are building our software kind of as we go, and we're sort of trying to see where those two approaches end up. So I want to give a quick overview of what we have in Charm. So these are the basic components. At the very bottom of Charm, we have these CMath libraries, which I mentioned, which do the kind of the basic computational operations. And a little bit above that, we have some Python wrappers for these, which give you some abstractions for dealing with groups and rings and fields. And so we have some crypto base operations. If we need to access ciphers, we need to do encryption efficiently in some mode of operation, we can use that. We have a benchmark module, which is built into the code that allows you to benchmark not only the performance of a piece of Python code, but also to count the number of operations that have been used in a particular run. You can actually specify at a very granular level what you want to count. It will also allow you to measure only the performance of the C code. So if you feel that the Python code is actually some huge overhead in your particular application, you just want to see how much time has been spent down here, you can limit that in the benchmark module. But above that, we have a lot of reusable components. We have a library of schemes, and these schemes are designed so that you can build protocols out of them. We have a protocol engine, which is designed to sort of do all the basic infrastructure if you need to implement interactive protocols. We have a kind of a reusable toolkit of Python code that does a lot of things like linear secret sharing, all these basic tools that you need to implement things like attribute based encryption. And at the top, we have an architecture called the adapter architecture that deals with cases where you have two schemes that are not directly compatible, but you want to use them together in the same protocol. So you have a signature scheme that has one input space, and you have an encryption scheme that has a very different input space or output space, and you want to use them together. So this is our answer for dealing with all of those cases where you would have to normally write ugly glue code to get different libraries to work. So I mentioned the base modules. We use a lot of standard code to do the underlying math routines. We use pairing-based crypto. We're moving to Miracle. We use GMP and so on. We provide Python extensions to do most of these things, and we are currently, and I say in progress, meaning that we're currently thinking about what to do in terms of adding Lattice support. We have this benchmark module, which is designed not to induce a lot of overhead. It's basically designed to make it as easy as possible for a developer to add to a program. You can basically say, okay, let's say I want to measure the number of multiplications, exponentiations, and so on. And we have this ability to sort of compare schemes with that. The way that you would use it is you say in your code, okay, init the benchmark module, start the benchmark module now, and then specify all the things you want to measure, and then end the benchmark module, and you can basically dump those results after the fact. Essentially, it keeps a database of all of the various counts that it has. The Toolbox has a lot of different things in it. We have code for handling things like certificates, padding, encryption schemes. We have key and ciphertext serialization, which tends to be very specific for different formats. All of the secret sharing things, encodings, for example, padding schemes are also in there too. we're really hoping to build this toolbox. And our approach right now, because we're working with a language like Python, is that we implement a scheme, we see which parts of it are likely to be reused, and we move those into the toolbox. And over time, we've actually built up a toolbox that's now to the point where we rarely have to add new code, but when we do, it grows a little bit. We have these abstractions for algebraic groups and so on. So kind of the meat of this is that in a very, very short time, we've been able to implement a huge number of schemes. Now, if you think about the total number of schemes that have been implemented now, it's probably on the order of 24, if you think about the various libraries out there. So in the course of a week, we're now able to implement 12 schemes. Basically, just find a research paper. If it's in one of the settings we support, we can translate it. We have this library that we're sort of building right now with some of the basic systems, group signatures, identity-based encryption. Because of Brent, we've now been forced to implement 3 different attribute-based encryption schemes, including a distributed attribute-based encryption scheme that he recently came out with. When I found out he was giving a talk today, I was considering spending the weekend implementing his latest scheme, but I did not do that. All these various pieces, including protocols and so on. Just to give you an idea of what it looks like to implement a scheme, here is a just kind of brief listing of a few of those things that shows the number of lines of code we had to write to make these actually happen. It's usually very small. So I want to give a quick example of what it means to implement a scheme, and that kind of will give an overview of some of the basic features. So we want to implement a new scheme. Let's say we want to implement the Kramer-Shoup encryption scheme, which most people are familiar with. So we create a class. And this class inherits from a standard base class called pkenc, which has a defined API. We define an initialization routine, which is responsible for taking care of setting up the parameters. And then we define a set of standard encryption scheme algorithms, keygen, encrypt, decrypt. These are things you see in every modern research paper. And then you write the algorithms. Again, there's nothing radical here, but this just gives you an idea of kind of what you have to do. We have the ability to grab random elements from a group, random elements from different groups, and we can basically put these things together, do a few exponentiations, pack the results into ciphertext, and then return those things in a data structure without having to do anything painful. Here's another thing where we have a built-in routine for encoding messages to different groups. Again, most of the same stuff. We're taking in a public key and a message here, and we're returning a ciphertext in this particular format. We use Python dictionaries to encode most of the elements so that it's very easy to recognize a ciphertext when we get it back. We don't have to worry about what order it's been put together in. We can just basically say, here are the elements that we want. Yes?
Does ZR have some special meaning?
ZR is, in this particular implementation, we are actually using, R is the order of the group, so we're using a prime order group here. This is just our abstraction for prime order groups. And this is it. And again, there's not too much here. The only thing that's really interesting here is that we are actually hashing something. So we have 2 different groups here. We're hashing something to an integer group, and we're hashing these values. This is the kind of stuff that when you write it in C, again, it's not super novel when you think about it from a high level. The minute you have to write this, the minute you have to deal with how do I serialize 3 group elements into a buffer, hash them, take the results, and transform it into an integer, it's extremely painful. You're looking at 20 lines of code. We can do that in 1. So just straightforward things. Yes?
How do you guarantee that these encodings, from a security point of view, you want to make sure that the serialization is uniquely parsable, right? Because otherwise you can get collisions and sort of funny ways. How does that happen?
So right now, I mean, there's nothing, it's not terribly sophisticated. This notation here indicates a particular way that we're going to serialize these group elements. So essentially, it's basically take them, write them out into a particular string of bytes. We know how long that will be, concatenate them as a buffer.
So you do it by fixed length encoding?
That's exactly right. Yep. So there are potentially ways that we could make this a little.
If I have a variable length, so I mean, I had to struggle with this usually. I have a variable length message and a fixed length something, another variable length field. Once you have 2 variable length fields,
yep,
you actually have to think about it.
We do.
Do you take care of the thinking?
We don't take care of that kind of issue yet, but we can in the future. It's a good thing to know about. So again, decoding and so on is all here. I want to give one more example just to show the kind of things we have in the toolbox. We looked at an ABE scheme today. Yes?
So sorry, I have to leave in a second.
Yeah, okay.
So one question is, have you submitted this work anywhere yet, or what's your plan?
We have a tech report of this one.
Yeah, so just one comment. Like, actually, I really do like the idea. Like, I think it's, I like the scheme, of course. Like, I wonder though, for this is just kind of a general thing, and I don't think it's like for a conference. Are you going to go for a security conference or a crypto conference? Because for a security conference, I could guess that they're like, oh, all these schemes. I don't like. I think what's really cool is that you cover all these schemes, right? And you can cover them easily. But I'm not sure if like the Usenix reviewer knows what.
There's no way this is getting into a crypto conference. This is not something that cryptographers want to publish. I mean, this is not the kind of work that exists there.
So it's not getting into a crypto.
I mean, this is not going into a major crypto conference. This is you very rarely see this work. Maybe you see
into a major security conference.
Yes.
That's the question. Yeah, it's a big problem.
I think you can. I mean.
You want the program thing?
I think
no, I just mean. I mean, we did something
Yeah.
fairly similar, and I think you can really sell it.
You think you can? Oh, it's
I think this would have been a great Usenix submission. We just didn't have it ready by Usenix.
Yeah, I mean, I do too. I just wonder.
Yep.
You know,
So what is
split
the
the team
so now you're asking
into
more
two,
philosophical questions. What's the venue for this kind of crypto engineering?
Yeah.
I don't know what it is. I wish
And
I
I
did.
don't mean it in a negative way. I mean it like
No, it's a
like
big
it'd be
problem.
Nice to figure it out way.
It's a big problem. Yes.
Another community that might be interested is programming languages / software engineering. Actually, which raised a question. I was wondering, by choosing Python here, isn't it a little unfortunate? There's a whole line of work on taking languages like ML and these things and doing formal verifications and engines for analysis. And why did you? It seems like you just missed what could have been a really nice opportunity there.
So let me.
Having another dimension of analysis you could do on this.
So first of all, the answer to that is I don't think that using Python precludes formal analysis. A lot of people say Python's not a strongly typed language, but that's you can deal with that.
But are there any engines that support formal analysis of Python?
No, there.
People have worked on other languages.
Sure, there aren't. But a lot of the engines that are out there are working on very specific functional things like we have one at Microsoft here, which is used to do DKM, which was yeah. So let me put it another way: the places where I've seen these formally verified languages used to deploy actual shipping crypto systems, the products, they could fit in this cup. It's never happened. The reason is because when people actually want to ship things, what they do is they do a formal analysis, they implement it over here, and then they re-implement it in another language. They re-implement in C#, they re-implement something that you can use and developers know how to work with. And so our philosophy is that, maybe I'm being a little blunt about this, but our philosophy is that these languages are very, very useful, but if you don't employ a language that developers are willing to use and companies are willing to ship, and people are actually comfortable with and are well supported, you're really doing academic work that isn't going to advance the field very much. I mean, the formal verification itself is very useful, but when it comes to applying it to a language, we should be applying it to languages that are likely to be used. And maybe that's not nice, but I really think that's important. And this is the problem with DKM, is they have two implementations. They have I guess it's ML, and they have a C# implementation. One hopes that these are the same thing. One hopes that there's a direct map between what's been analyzed and what's going to ship. Can anyone here tell me that's the case? And there's
What would be your strategy for solving that problem? Would you do that for Python?
I would like to do that for Python. I would like to take that kind of formal verification work and move it to languages like Python. I don't think it's impossible. I don't think it's also required for many applications, but for those applications where it is, we should be able to support it in a language we can use.
Okay, but I'll stop after this.
Sure. Formal verification is
You have to solve the same problem, but you have to go down a path no one's ever gone down before.
Yep.
Whereas the DKM thing is an example of where that's been shown possible
Yep.
with ML.
And I think that there's some great feasibility results out there, but I'm probably offending a lot of people. This is going to get out, but I look at these more as feasibility results. They're not going to be practical results until we can do them for languages that people are willing to use in a broad, wide scale. Anyway.
Well, I just wanted to comment. So Brent's question, in some sense, is getting at this issue of incentives. So you said in the beginning, why don't people do this? And this question of incentives. So the issue with, in industry, obviously, there's a great incentive to build these libraries,
Right.
but then you're not generally allowed to share them with everyone else. And so, one of my questions is kind of what is your intention with this library? Like, are you going to release it publicly and if so, under what license? If you're building on those other pieces like GMP and stuff, it could be restricted by what licenses they release. I mean, there's this whole huge mess. Like Sage has dealt with this. The Sage community has come to blows over, these issues. And I mean, they're not easy problems to solve.
So our goal has always been to release this publicly under probably LGPL, which means that the library itself will be GPL'd, but you can use it within another product without having to worry about that product also being GPL. And so far, with a couple of exceptions, we've been able to do that. I'm going to have to plug my computer in before it dies. But that's in fact our major goal. Another thing that I'm going to say about this is that our goal here is to build a system on top of which we can do research. The system itself is really a basic level, and we'd like to continue to reuse it. Again, it's not so much that we're trying to publish the system. We would like to have a system that's kind of usable and everybody else can use as well. It's very necessary right now for the work that we're doing with the Sharps grant that we have a system like this. So if we don't have a system that allows us to build crypto systems easily, we are going to be kind of in trouble.
Oh, I see. So there's actually a huge incentive there, right, which is proof of concept in a particular setting, which is an enormously important setting, which is that healthcare.
Yeah, Sharps also gives us some funding to do this with so that we can push this out. And when one of the project objectives is things that can be useful to the community.
Okay, so there's, I'll skip past this thing. I wanted to quickly give at least one slide from encryption in an attribute-based encryption scheme. My implementation of this in C was only about 1,000 lines, so this is a big improvement. Couple of things you'll notice is that we have some very important library routines. We have this create policy, which takes in a string. Attribute-based encryption policies are typically strings separated by ands and ors, and we use that across many ABE schemes. So why not just put that in our toolbox so we can reuse it? We have this get attribute list. We have the ability to calculate shares, and this is all standard secret sharing code that we just reuse over and over again for every ABE scheme we have. We could use it if I was implementing Brent's Hive. We'd use that again. So there are many things that we can use. Again, the objection here is that we're hiding pieces of code, but these are pieces of code that are themselves not very long, and we have used them for many different schemes. So it's not totally an obvious objection. And this is decryption, which I won't go into too much detail, but again, we have a few library routines. And what I want to just kind of get at is that much of what you see up here in LaTeX maps directly to what you see in this code. We prune the tree a little bit, we get the coefficients, and then we have this for. Everything in the prune list, we do this, which kind of maps to this product up here, I think. And then we do a final line, which is just this decryption.
So,
yes?
So I'm sort of curious who you're expecting to be writing this code. So I mean...
You.
Okay, so there's sort of... Well, I mean, there's the cryptographer, right? And this is certainly making the job easier for them. You know, they wrote up their paper, and now they don't have to go hack around and see, which they haven't used in, however many years. But, I mean, the incentive still isn't there necessarily, right, for the cryptographer. I mean, they publish their paper, it's like this theoretical contribution, and then they're on to the next one. And so the question is, I mean, so...
Who's going to do it?
So you would think that it would be the person who wants to plug it into their thing, but then my question, and I don't know if there's a good answer, I mean, is it safe in some sense for someone who really doesn't know crypto? They can say, okay, well, they can go look up the paper and they can do this mapping themselves, but maybe they mess something up and then it's completely insecure. I mean, so how do you sort of...
So there are two answers to that. One is that I think that the grad students of the world, hopefully, the crypto grad students of the world will hopefully help a little bit with this. In the short term, we're actually working on it. If you have a scheme and you'd like to see it implemented, if you just for vanity's sake, you'd like to see it implemented, come to us. We're happy to do it. It takes a couple hours. It's not a big deal. In the longer term, though, there are two levels of this. One is implementing these basic schemes, which I agree takes a lot of knowledge. Now, the next thing is, let's say you want to build a protocol. You're not an expert. You want to build a protocol. Maybe it's a simple protocol. It's encryption and signing put together. How do you do that securely? How do you know what these schemes provide in terms of their security definitions? Can I build something that does these things? That's an area where we think less expert people will be available. So we do have some ideas there on how to make that easier for non-experts so they can't screw it up. Okay. And I'll come back to that. But yeah, I agree. At some point, you have to understand the scheme. But let me put it this way. If you could implement this scheme in an hour, instead of, how long did it take you to write your verifiable encryption scheme in last year?
You mean just in C++, not after we wrote
Sure.
Interpreter?
Yeah.
I suck at programming like months.
So that's what I'm saying. We're trying to lower the barrier of entry, the barrier of having to code this kind of stuff, to the point where maybe it's not such a problem. Maybe that won't be the solution. We'd like it to be, but who knows? So let me get to the next aspect, which is.
Generate C code out of this?
Yes, so that's one of the things that we're working on now is we're using some Python to C compilers along with our code to actually translate that Python code to efficiency. We think that's going to be important in terms of actually deploying things to products.
If Python is only this upper level,
yeah.
It's not very doesn't matter.
Yeah, well, that's the other thing. So you could also just import the Python interpreter into your application. It's not that big. We've been experimenting with that too. There are different ways to get this. So when you see our performance numbers, you can decide whether or not you believe in it, but we'd like to be able to do that. So we have a few things that we have put in place to make things easier, to make it difficult for people to make mistakes. And one of them is that we have the scheme class hierarchy, which we just start with a few standard APIs. So we have these things that everyone knows. But beyond that, we want to annotate schemes. So once you annotate a scheme, we'd like to annotate it with various things that are useful, like what complexity assumption does that scheme use in its security proof? What computational model does the proof use? What security definition? And this is probably the most important thing. You're implementing a signature scheme. Is it strongly unforgeable, weakly unforgeable? Exactly what is the definition? Is it a one-time signature? So these things actually are carried with the objects that you create. We also have very important things like the input and the output space. So you have Waters IBE, which takes in a vector of bits as the ID space. You have other IBE schemes which take in strings. So you'd like to be able to map from one to the other. How do you do that? Well, we have to annotate the scheme and say, this is our input space and this is our output space. Then you can combine the schemes. Now the question is, what do you do with this information? So you want to combine a bunch of different schemes to build an application. How do you do that? So you have all these different data structures and you may have incompatible inputs and outputs. How do you make it so that you can actually connect these things without writing glue code? The answer we came up with is something called adapters. And adapters are largely responsible for the task of taking different kinds of data type. Like, for example, I have an identity that's a string and I want to encode it into something I can use with a Waters IBE. Its job is to actually actively query that scheme and say, what is your input type for the ID space? Find out what it is, and then figure out exactly what it needs to do to translate whatever I want to put in as the ID into something that can be fed into the Waters scheme. So we have this idea of kind of code that is, I wouldn't say intelligent, but is at least aware of other components and can adapt itself properly. Other things we can do with adapters, we can actually use them to implement more complex protocols. There's a whole class of transforms called IBE to PKE transforms that take in an identity-based encryption scheme and sometimes a MAC or a signature and actually build a CCA secure public key encryption scheme. There are many protocols like that. So we can build generic adapters that basically you just feed them two schemes, a signature and an IBE, and they will decide whether or not those schemes have the necessary security properties to build a higher level scheme. So there are many different things you can do. We can do hybrid encryption with an adapter. If I want to encrypt long messages, well, I have a IBE scheme or a public key encryption scheme that takes short messages. This adapter handles all of the work of taking a large message, generating a random session key, then using a cipher to actually do the payload encryption. So there are many different things that you can do with these adapters. And the idea is that ultimately we're going to work towards a place where we can make these more automated. So I'll give you one example. I already gave you the hybrid encryption example, so I'm not going to talk about this. But so let's give a very specific one, actually. So we have this application that needs to do hybrid encryption. Bulk data needs to be encrypted. And so what we're going to do is we want to use an IBE scheme to encrypt it. So we want to basically build an adapter. And so the example I'm going to start with is the Bonnet-Boyen scheme from 2004, which we've already talked about today. Two of the details of the scheme are that the plaintext space is in a group. It's actually GT of a bilinear group. And the ID space is an integer. Now, that's not exactly what I want to use for my application. So I can put in place an ID space adapter. And all this does is it applies a target collision resistant hash to the identity that I've given it. So the identity is now a string. There's nothing, an unlimited string. It gets hashed down into this integer. There's nothing really interesting happening here. But it has a couple of kind of weird side effects, one of which is that if you're willing to analyze this new scheme in the random oracle model, you've actually taken a selectively secure IBE scheme and you've converted it into a fully secure IBE scheme. Not a big deal, but now if you actually query this and you say, what are your security properties, this will report that it's a fully secure IBE, as well as the changed interface. Next step is we could just bolt on another adapter to this. So we want to do hybrid encryption. Well, this will take in an arbitrary plaintext space, the same ID, pass the ID through, but do the hybrid encryption to move that data. So this is a very simple example. And this is what it looks like to instantiate these things. This is our IBE adapter. So this is what encryption is. This is hybrid encryption, I think. So this basically does cipher encryption, instantiate to cipher, and we say CCM. This doesn't specify it's AES, but that's what we use right now as a low level. So here is an example of the CHK04 transform that takes a selectively secure IB and a one-time signature and converts it into a PKE, a CCA secure public key encryption scheme. So we're actually using a couple of things here. So we have this issue. If you're familiar, how many people are familiar with a CHK transform? So the basic idea is that you generate a key pair for a one-time signature, and you use the public key as the identity for an IBE scheme when you encrypt. Now the problem is, if you look at the Bonnet-Boyan scheme itself, it can't necessarily take whatever that public key is and use it directly because it expects the input to be an element of ZQ. So we apply this ID space adapter, and that allows us to take those arbitrary strings. Then we have the one-time signature, and this code is very, very, very small. All it does is the actual work of implementing that 8 or 9 lines that represent the CHK scheme. It generates a key pair from this, uses the public key to encrypt the message, and it signs the resulting ciphertext using this, which involves yet another conversion of data types, and it returns the ciphertext and it returns the signature, as well as the public key, which is the ID. Yes?
I guess I'm going to ask the serialization question again in this context. Right? The conversion of data types has to be uniquely parsable, so that a public key for this signature, one-time signature, doesn't also look like a public key in that one-time signature. If I can play around with the order. What do you do for? I mean, the industry loves ASN1 BR encoding rules, some horrible things.
So in this case, it's not as much of an issue. Because in this case, you're actually allowed to query on just about anything. If you can make it look like a different public key, it will just look like a different identity. When you try to decrypt with that IBE scheme, it won't decrypt. So this is not a case where you have to worry as much. But you're right.
You're relying on a very specific sort of security proof type thing.
Exactly. So for this case, that wouldn't be an issue. In general, we do have a very specific serialization set of rules that, again, right now is fixed length. But we basically say, if you put these things together in this order, so they will be serialized in this order.
So you don't do something like ASN1?
We don't, not now. But we could in the future. Right now, we don't. So, so this is, again, we have this public key. This is just an example of how you can keep throwing these things together. We add hybrid encryption. So now we have a CCA secure scheme. Okay, so this just goes on forever. So we also have this dictionary. So many of these security definitions imply other security definitions. So a strongly unforgeable one-time signature implies a weakly unforgeable one-time signature. A strongly unforgeable many-time signature implies a one-time signature, and so on. To make these rules work, we actually have to tell Charm about all of these things. So we have rule engines that allow you to compare and see if things work. We also have complexity assumption equivalences and so on. So we had to make the system aware of these notions in order to build these systems. Now, the vision of this is that right now we may have 20 different schemes. But those 20 schemes can be used with adapters and other systems to combine to make many different protocols and many different additional schemes. So our kind of vision is that someday you're going to be able to say, I need a scheme that has this functionality under these complexity assumptions. These are my input and output requirements and security definitions. And it's going to basically output a list of schemes that it can build from known adapters. The applications of this may or may not be useful, but this is kind of where we'd like to go. So you don't have to go out of your way to put these things together. They just get assembled for you when you need them. I like this, but most people may not. So interactive protocols. This is a very, very important thing. I work in the area of interactive protocols. Very, very hard to deal with this stuff when you have to write everything from scratch. What does it take to build an interactive protocol? Well, you have to have some kind of database or internal memory to maintain state. You have to serialize data, which you just mentioned is a horrifyingly awful process. You have to do network transmission, which is not so bad, but it takes a lot of work. Then what happens if you have a sub-protocol? So when I write an oblivious transfer protocol, it has a zero-knowledge proof in the middle of it. Well, then I have to jump out into that protocol, complete the execution, come back with the result, and then move on. Writing that is not a lot of fun. So we need some way of making that transparent to the developer. The developer doesn't, these protocols mostly look the same, so let's provide some templates for people. So let's talk about what you have to do to set up a protocol. I'm going to start with an example here. Very simple protocol that most people know, the Schnorr HVZK. So we set up the protocol. Looks a little complicated, but it's not really that complicated. We just say, here are the states, and here are the transactions, and basically, here are the parties. The one thing that we have to provide to the system is basically a socket interface that says the person you want to talk to is at the end of this socket. So this protocol, incidentally, describes both the states for the prover and the verifier. This class that I'm building describes the entire protocol. When I instantiate it, I will say, now I want to be the prover, and I want to talk to this person. I want to actually run this protocol. Okay, so this is what you actually have to implement. So all you have to do is give a list of the states and the functions that are going to implement the core of them. And then this is kind of all that you have to do in terms of actual code writing to implement the guts of this first state up here. You use built-in store functions to keep values that you want to use later. And then you return from this function with the stuff that needs to be pushed over the wire. So the entire protocol is this few lines. Right? And you have to do this for every single state. Okay, I'll skip the states. They all kind of look like this. So that's fine. But there are a lot of protocols where you have to actually implement the protocols yourself. There are others where there are sub-protocols that are not given to you in the paper. This is a classic example of an anonymous credential protocol. Protocol is kind of here. You go through these steps, and then you hit this point where you say, execute this zero-knowledge proof. Anyone off the top of your head tell me exactly what the protocol for implementing this is? It's not easy, and Sarah actually worked on this last year. She came up with a compiler that does this for you automatically. Well, this is not a new idea, but we can use that as part of our system as well. So we can take this complicated proof, and we can spit out something that directly maps to that basically implements that protocol, that full interactive protocol. The only thing that's different from what you did is that where she had to write her own interpreter to actually handle the compiling and the interpretation of that proof, we have an interpreter. We have Python. So all we have to do is basically when we hit this line in the protocol, we just build a bunch of Python code and we execute it dynamically right here in the compiler, in the interpreter. So this is what it looks like from the prover's point of view. You set up some public variables. You set up some secret variables. You tell it who you want to talk to. And you make one call. This call will handle all of the work of compiling that zero-knowledge proof into Python code, which itself is in that protocol structure, which you can then execute. It will then run it interactively with the remote party and come back with a result. So this is a much closer map to what you see in a research paper than what you might see if you have to set up all this other information. Now, why do we do this dynamically? Why not compile this proof one time before we run the protocol and use it? Well, the answer is that there's information available to us now that we have the protocol running, where we have all of these values, where we can basically say, well, what kind of setting are we running in? What kind of group elements are these? Are these integers? Are they elliptic curve group elements? There's a lot of information that's not available to you before you run the program, that will be when you get to this point. Your ZKPDL, Sarah's ZKPDL, actually requires you to specify a lot of this stuff in advance. So we just wanted to get rid of that and say, well, you're already running this protocol. Why specify it twice? So let's just have that information available to you by an introspection. And this is what the compiled code looks like. It's not pretty, but this is a very simple proof, and this is kind of what you get at the end. So I already sort of showed you this. So I want to point out that there is work. So Sarah's ZKPDL is something that does this. There's also the CACE, which is a sophisticated compiler, which does stuff in advance. It uses a much more complicated language to specify the proofs. They do have a nice formal verification component, speaking of which we hope to kind of leverage in the future. So people ask me about performance measurements, and I think this is kind of the key. Is this something that you want to do? The answer is sometimes. This is our implementation of ECDSA. So this is OpenSSL's native code optimized, and we used the built-in speed test program to see how fast it runs. Okay? We have C right here, and we have the Python version that uses some C code as the optimization, but is written in Python. Not very good, is it? Terrible. I mean, when you look at it, we're about half as fast on verify, and we're even maybe 4 times slower when it comes to signing. But if you look at the actual timings here, they're not very high. So if you have to generate 100,000 DSA signatures, ECDSA signatures, don't use this algorithm. This is not the right tool to use. But if you have to generate 1 or 2 in the course of a protocol, why are you going to take on all sorts of extra overhead just to generate a few signatures? But if you look at more complex protocols, and the difference here is that these protocols use much more mathematically intensive operations. This over here is the Bethencourt Attribute Based Encryption scheme working with a policy of size 50 nodes. The differences here are not that big. Really, the only difference, there's no difference in key generation time between our code and the native optimized C code. There is a difference in encryption time. And we found that that difference is entirely due to a parsing library that we use to parse policies, and we're actually trying to fix that. But there's not very much difference in the amount of time that we spend doing actual operations. Decryption is almost the same. So depending on what kind of operation you're doing, are you building something that does a mode of operation for a cipher? Do not do it in Python. But if you're doing something that uses more powerful operations like lots of pairings, then this is fine with very, very minimal cost. Yes?
ECDSA is a big surprise. The dominant operation is an integer exponentiation, which you're doing in C either way, right?
Yep.
Because the Python code doesn't do the loops.
Yep.
The Python code just calls C to do the exponentiation.
It doesn't do the loops inside the exponentiation. But when you think of the call overhead, so the exponentiation and the point multiplication is so fast that when you're in Python and you have to think about our call overhead in Python, it actually becomes a significant part of the cost.
Really?
Dealing with work like serialization and all that other stuff that we have to do in a very simple routine really does become significant. When you're over here, the costs, all the costs are still there, but they're not relevant. So yes.
So part of the reason why we, like you said, have specify a lot of stuff ahead of time is so we can do optimizations for like multi-base exponentiation.
Yep.
Can you guys do anything like that?
Sure.
I mean, okay. So
the only thing that's different, so we have all the information that you have. The only difference is that we get it by looking at the variables that have already been allocated.
Okay.
So what information do you need that would allow you to make that optimization?
Well, for example, I mean, so I'm obviously not much familiar with the library, but if I'm doing like 20 proofs using the same, G and H bases every time,
okay, that's
right? True. Then in CKVDL you can cache all those powers,
yep.
And like the first proof is going to be like more time intensive, but then it's like, I mean, it's a huge speed up. So if you're doing everything dynamically, it seems like.
That's true.
Okay, so you can't magically do that, or can.
Well, I mean, you would have. You're right. For that example,
you can do the optimizations like at the time, I assume, right? But I'm saying you can't do it like from one thing to the next in some sense.
You're right. So I mean, basically, you have to say that I'm going to do 20 more of these, and you have to say you do this operation in advance. That's not something we can't know that you're going to do another 19 after that.
Okay.
So there are some optimizations you can't do. That's a good point. So there are some things we can, some things we can't. But again, I don't know, if you have to do 1,000 of them, that's going to be an issue, but not every case that you have to do that. Again, and the other thing that's worth mentioning is that you can take our compiler and you can use it in advance. You can specify optimizations, you can do those in advance and just generate code. But that's not really what we've done. So a couple of other benchmark module results, I just want to point these out. So this is the kind of stuff that gets spit out of our benchmark module, the number of exponentiations and so on. This is Waters' encryption from his 09 paper. 152 exponentiations for a 50-element policy, 345 multiplications, and in the decryption operation, 101 pairings is what we had to compute. And we have total time that's spent, I believe this is total time spent with the benchmark on, with the benchmark off. So this is the kind of output we can produce. Few statistics before I end, just to give you an idea of how much smaller this is in terms of code size from anything we've produced before. All of our schemes and all of our adapters are less than 2,000 lines of code, and I think that probably overestimates a little bit. Our benchmark module is a few hundred lines of code. Our toolbox is less than 1,000. So really, it takes much, much less code and much, much less work, and it's much, much more readable to produce this kind of stuff. So we're using it right now in these medical record research projects where we found that, again, the overhead for these things, the Python overhead is negligible in all of the use cases that we've come up with. We expect to use it in all kinds of different other applications we come up with. We have a request from SRI to implement a distributed scheme, a distributed ABE, which we worked out a little while ago. And we're actually hoping to hire a full-time developer. This is one of these tricky situations where having grad students do work that is largely engineering may not be the best use of grad students, so we're actually hoping to hire a full-time developer to support this and keep it supported so that other people can use it and it won't end up being one of these orphan projects. Last thing I will say, and a lot of people have asked about this, what is left to do here? There's a lot. We can optimize things, we can add more schemes, but really what I don't have on the slide that I do want to talk about is we're now working on adding a formal verification component. And the first step is to make sure that things are strongly typed and that we can derive types automatically and then have you correct them. So that's a big thing. We're also working on some current work that involves signature batch verification, where we can take a signature verification algorithm, programmatically analyze it, apply some rules to it, and generate a batch verifier, which gets automatically coded into Python on the fly, so that depending on the input we take in, we can actually produce these things and execute them. The hope is that using this whole system as a base, we're going to be able to do a lot of sort of more fundamental research that we think will be useful. And here is the URL if you ever want to check it out. Put the slides up, and that's it. Yeah.
So one of Python's other charms, if you will, is the ability to do easy visualization. Is there any way that would be beneficial here? Is there some way that you'd help people visualize how these protocols are interacting, given that you already have it in this?
That's a really good idea, but no. It's a great idea, though. Yeah.
You touched on this very briefly, but the fact is that Charm is a kind of top-level language, whereas the libraries here are likely to be kind of underneath something else, right? So that, kind of using a glue language at this level has some inconsistency with the way one typically thinks of glue languages.
Sure.
So, but maybe that's okay. But to test that, you need to use this in applications that intensively use cryptography.
That's correct.
And there, I think the concerns would be going out and entering the Python runtime,
right,
in tight loops would be very costly.
Yep. So that's something that we're actually working on. We're looking at the cost of that. It's not as bad as you think it'd be. If your purpose here is to really do intensive crypto, maybe this isn't the tool for it. But if your tool is, if you're trying to prototype something, you want to prototype a server that does interactive protocols, oblivious transfer, any kind of anonymous credential, this is a really nice tool. But we think that, and that's also the reason we're looking at using Python to C compilation, is so we can eventually move that Python interpreter out of things.
So some schemes need particular parameter choices. So
yep.
You can't just use any two primes, you can
sure.
use special two primes.
Yep.
So where do you wrap that up? Is
it depends.
Generation, key generation?
Typically we have an initialization routine where you can specify the group setting that you're using. Right now the schemes don't actively check to see that you haven't. So for example, if you give it a bilinear group where DDH is easy, many of these schemes become insecure. So we don't actively check for that kind of thing, but we're actually hoping to annotate the groups and say you can provide any group that has where these assumptions are believed to hold. That's going to take a little bit of work, but it's the kind of thing we want to do to sort of bulletproof it to make it easy to switch from setting to setting.
I have a couple of comments that I'd be curious in your reaction to. So apologize if one seems kind of positive and one seems kind of negative.
No, it's okay.
First of all, I want to say, this is totally awesome work. This is really great. For example, William Stein in the Sage community has been asking for, who's going to use Sage to build crypto and what do you want to see built and stuff like that. So in some sense, you've answered that call already. And on both of these comments are kind of around the question of incentives. So I think it's really cool that we see this confluence of the application of the crypto with the healthcare scenarios. That I'm not saying that all of your funding necessarily came from sharks or whatever, but that
don't tell Carl.
Here's a setting where there was a huge incentive to actually have these crypto protocols built. And so federal funding, it may have even been kind of roundabout that it came to this project, and yet now that this exists, it's going to have it could potentially have a huge impact not only in this setting but in other industries, and also a huge public good or benefit. For example, I can think of scenarios where two companies are negotiating over crypto protocols, and it's difficult for people to, release their proprietary, code, or they may want to share it, or they might want to have some independent people, doing evaluations or figuring out, negotiate how to, bring two different solutions together from different companies. So for interoperability, which is a huge challenge, for the application of crypto protocols. So I see the application of this as potentially much broader than the setting in which it was, able to kind of spring up. And it just seems like more broadly that it could be an argument for federal funding. I mean, you might ask, why hasn't crypto development been federally funded so far before? And you might speculate that it might have something to do with NSA or something like that. But I think this is a great argument for, this type of project.
Yeah, I mean, this project was born of necessity. It's not how I would be using my research time if I wasn't facing the prospect of building a lot of crypto systems. It's not, it's not the kind of work that's going to get you crypto papers, but it's really important anyway. And so I think we're just going to keep going with it and make sure that the tool is solid and that people can use it. And hope that the next time I give this talk, you guys are saying thank you for building this thing, but we'll see.
Yeah, to comment a little bit on this incentives question. One of the shifts here is that ordinarily these research grants are driving publication and conference proceedings, whereas we don't really get much credit for publishing and conference proceedings. We get credit for influencing a vendor.
It's awful.
So that's the kind of thing that actually looks good for that if something like what you just described actually happened, that would be a sign of hey, really that helped. So.
Yeah, we want to build things. I mean, we have to make them HHS happy at this point.
Well, my second comment, I made a strategic error. I should have made the negative one first. So on the negative side, I mean, one thing that I am kind of fascinated by that in the industry, what you see is this huge lag between proposals of cryptographic protocols and systems and things and adoption, right? So 15 years, kind of minimum. So accounted for by inertia, but also a lack of trust in new assumptions and giving the community time to whack away at crazy assumptions that are being introduced all over the place.
Sure.
And so one danger that I actually see here is that with the ability to quickly, so Brent publishes a paper and tomorrow you can have an implementation of it. Somebody else can grab this and start using it. And that lag, I see that as an actual real danger, that there was actually something very sensible about having this huge lag in adoption.
So I agree that maybe a year or two lag. Well, maybe that's a comment more on the assumptions that we're using now than on the new crypto system itself. I think a year or two lag would make sense, but I really think that it would be nice to see the open source community start to use these things. I mean, IBE has been out now for 10 years. It's used by one company. And the reason for that is not entirely because Voltage owns the patents. It's because nobody outside of this community has access to code or the knowledge to use it. I'd like to see that change. And maybe there'll be some conflicting forces there. Some of it's patents, but I mean, what's stopping some open source project from, what's stopping, Bitcoin or some open source project like that from using IBE? Are they going to get sued? I think the reason is that people truly just don't know how to use the technology. I'd like to change that.
Well, and if the technology gets used, then more hackers will whack on it.
And that'll be
good.
So in terms of design rationale, even for picking Python, you're more so thinking about trying to find language that cryptographers would use, or that developers would use, or that grad students who have been minion developers for the stipends would use?
I have been meaning to rename this a programmer-focused framework for application development, because everything about this has been from my point of view of, let's find every single tool should be based on what makes it easy to develop things. And we looked at a lot of languages. Util Intel's using Java. I think that's great, but I think that Java is the wrong choice. I think that things need to be as simple as possible to make them used by lots of people. That's why we chose Python. We looked at Lua too. That was not a good idea.
And then the second question, obviously, if you're intending free brush use for production, then precisely if one of these schemes ends up being compromised, revoked, when it doesn't work, is there any thought of making sure that the layer of abstraction that everyone above it who's using it is you capable of just switching it by a configuration or something versus, well, great, now my product doesn't work. I have to spend X number of months.
I think that adapters might be a way to go there, because if you need to switch out this signature scheme for another one, right now that's awful and painful. But here, you should literally be able to change one term in your code and have another signature scheme may not be as efficient, but the code will function.
Other questions or comments?
I'd just like to say that I'm really impressed.
Thanks.